Yeah. So, okay. Let me just start by saying a little bit about me. So I work at NTNU in Trondheim. Let's see. This works better here. And the focus of my research is mostly the origin of ultra-high energy cosmic rays. And by that, I mean phenomenology and building models for where ultra-high energies may be coming from, and the phenomenology of sources of astrophysical neutrinos. And specifically, I work most on active galactic nuclei as sources of high energy radiation in general. And so a lot of what I'm going to say during these lectures, I'm going to use active galactic nuclei as an example, just because for me, they're the most exciting. Yeah, there are parallel processes in other source types as well. But maybe I'll have the most examples to give you from this field that I work the most in. Regarding the plan for the lectures, I'm aware that you are a very diverse group, so this makes it a little bit hard to have something for everyone. So the first hour, roughly, is going to be spent on rather general concepts, which are mostly experimental facts and very basic theoretical arguments about astrophysical neutrinos. For those of you that work on astrophysical neutrinos, this is going to be too introductory, but I hope to get everybody on board for what comes next. The second part, which we will cover today, is going to be about what we have learned in the last years about what generically what might be the sources of astrophysical neutrinos. So I can already give away that we don't yet know what are the sources of high energy astrophysical neutrinos, even though we've observed a flux of them. But I'm going to summarize what we've learned about the sources in the last decade. And finally, and this we will start already today, I'm going to go through an overview of all the popular, most likely astrophysical source candidates. And so today we'll start with active galactic nuclei, and we'll get to about halfway. And then on Wednesday, we'll continue and finish off. You see my list here, sources that I consider good candidates as high energy astrophysical accelerators of cosmic rays and neutrinos include gamma ray bursts, pulsars, tidal disruption events, and starburst galaxies. So we'll go through them one by one. Okay. So I have a few resources listed here. I hope that this is only the beginning of a long career for all of you in neutrino physics or astrophysics, and those of you who are going to go deeper into neutrino astrophysics. These are the textbooks that I like to use the most. So the first two are really specific to high energy neutrinos, and also this one, the second one, is also a good resource for high energy astrophysics and radiation processes. And then the third book I've listed here is one of tens of very good books on high energy radiation processes. But I've listed this one here because it's freely available on the internet, and because we're going to use it for one of the for the exercises today. So by far, it's not the only one. I'm sure you have other books on that topic. And then there are, of course, many excellent reviews, and they have, in the last 10 years, what we've known about astrophysical neutrinos has absolutely exponentially grown. And so likewise, a lot of the new things you will find only in reviews and not in the textbooks, which are somewhat older. So have a look around. Okay, I'm not allowed to move. Right, and please interrupt me, okay? So I'm very happy to have questions while we go along. So I start with this slide today as a motivation of why do we even care about astrophysical neutrinos? Because we have had for decades, for hundreds of years, in fact, beautiful telescopes which can show us the universe with great resolution. So why do we even bother trying to study the universe with neutrinos? And this is my one-page summary as to the motivation. Actually, neutrinos, astrophysical neutrinos can have various energies, but the ones that I will talk about the most today are high energy neutrinos. And so when we look at different wavelengths at the universe, we see different processes. So at very low energies, microwave, we see the photons left over from the Big Bang. Then at slightly higher energies, infrared and optical, we see with great detail, great resolution, the light from all the stars and dust. Then in the X-ray, again, we have fantastic angular resolution, and we see accretion around very compact objects like neutron stars and black holes. Then if we get to about GeV or TeV energies, we see radiation from accelerated particles. Here, the angular resolution of the observations and the sensitivity of the observations is not yet comparable to what we have at lower energies because we have so few photons. But still, we've seen a growing population of sources, galactic and extragalactic, in gamma rays in the last, especially in the last 10 years since the Fermi satellite was launched. But now, if we want to go anywhere beyond this energy of about 1 TeV, then we have a problem. The problem is that gamma rays interact with background photons from the cosmic microwave background, from the extragalactic background light, which is more infrared all the way up to UV, and they get stopped. So their propagation horizon at 1 keV, 10 to the 15 electron volts, is less than the distance from the Earth to the center of our galaxy. So it's almost certain that there exist sources of PV gamma rays outside our own galaxy, but we'll never be able to see them because of this problem. So you might have heard that a year ago, LASO announced the detection of PV energy gamma rays. These are from inside our own galaxy, and this is as far as we will ever get. So if we want to go higher in energy, our only chance is to use different messengers. So if we want to study the highest energy universe, we need to use neutrinos, which we've seen up to 10 PeV, very likely extragalactic. We'll talk about these today. And we will also talk about the connection to the highest energy cosmic rays, which we've observed with energies up to 10 to the 20 electron volts. Okay, so here, this tool is about all the places where we might find astrophysical neutrinos. So here is my brief overview, starting from the first known source of astrophysical neutrinos, which is, of course, the sun. So this is one of the two sources, only two astrophysical neutrino sources known. And so you all are familiar with this and the fact that in the sun, neutrinos get produced in fusion reactions, right? So we have the majority of neutrinos get produced in this first step of the proton-proton cycle, but they have a very low energy, which is shown here. And so experimentally, this channel was completely inaccessible to all the first experiments for searching for neutrinos from the sun. And then further in the cycle, if helium-3 fuses with the helium-4, then we have some higher energy neutrinos, especially if we get a boron-7 and then it has a proton capture, sorry, a beryllium-7 has a proton capture to a boron. And then that process, the inverse beta decay gives us a high energy neutrino, almost 8 MeV. And this is the first neutrino that was seen experimentally, you can see here, by the first generation of solar neutrino experiments. as well as this one, which is from this HEP cycle, this direct process in which a high energy neutrino gets observed. And this is the first, the image in neutrinos from Super Kamiokande of the sun. Very recently, I don't know if you're all aware of this, the Borexino collaboration, which has been measuring solar neutrinos for a few decades now, has finally released the results in the journal Nature, where they've measured the entire spectrum of solar neutrinos down to this process, which is extremely difficult to look at, to measure the neutrinos because of the backgrounds in the detector, radioactive elements, basically. Okay, and of course, you know that so this solar neutrino discovery led to 2 Nobel Prizes. First of all, just for the detection of the astrophysical neutrinos, and more recently to Super Kamiokande and Snow for the discovery of neutrino oscillations. So these were the first experiments that were sensitive both to the total number of neutrinos and to the number of electron neutrinos, such that they could confirm that what we're seeing is not a deficit of solar neutrinos, but in fact that neutrinos oscillate in Flavour because they have mass. And you'll talk all about this with Joachim tomorrow, how this happens. So briefly, the way these neutrinos get detected here, this is Super Kamiokande, the reincarnation of the original Kamiokande experiment, when a neutrino travels into the detector and it has a charge current interaction. It turns into a muon or an electron. A muon, if it's a muon neutrino that comes in, the muon has Cherenkov radiation, which produces this Cherenkov light, of which we see the signature here in the PMTs, which lie in the detector. So when we have an electron, the electron has quite some scattering, so we see a rather fuzzy image, whereas the muon neutrino produces this beautiful ring, and that's how Super Kamiokande can do Flavour identification. And somewhat similar, we're going to see in a moment, is what they do in ice cream to find the flavor of the incoming neutrino. Okay. So supernova neutrinos, I became aware looking at the program yesterday that you'll have a dedicated talk on this afternoon, but just briefly. So except for solar neutrinos and neutrinos from nuclear burning in sun-like stars, we also have a special channel for neutrino production in supernovae. Here is an example of a supernova in 1994. Mauricio, can they see my mouse on Zoom? Okay, because this is somehow, I don't know why it's not working. Okay, sometimes it works.
You can also see the light.
Okay, all right. So the idea, what happens here is that when we have a star much more massive than the sun, we have not only hydrogen burning in the core, but eventually the temperature gets high enough that we can have helium burning in the core, while we have hydrogen burning in an outer layer, and eventually temperature is high enough that we can continue to have burning of heavier and heavier elements until we have this onion-like structure in which we have iron in the center and silicon, oxygen, neon in the outer shells. And of course, beyond iron, the binding energy for nuclear drops again, so there is no going to any heavier elements. So at this point, even though the temperature is continuing to increase, there's nothing to do except to start some endothermic reactions in the core, which basically makes the core lose the pressure support and collapse. And the outer layers of the star explode into a supernova. So there we have a lot of neutrino emission. Nobody quite knows all the details, but we have neutrino emission also in the initial neutron star as a way of cooling, because it's an extremely compact object, so photons don't escape. And this led to another Nobel Prize for astrophysical neutrinos. So in 1987, there was a supernova in the Small Magellanic Cloud. And here you see the before and after of this event. And so 3 detectors, including the, at the time, Kameo-Kando detector in Japan, one in Baksan, one in the US, also neutrinos from that event. And this was the second confirmed neutrino source, astrophysical neutrino source. Okay, so, oops. Okay, I have transferred the PDF here, which I haven't done the build as I have found it, that's okay. So I wanted to ask you what other neutrino sources do. So these are the 2 neutrino sources we discuss, and they are down here. There are the cosmological neutrinos that you will discuss in Olga's lectures. What other sources of neutrinos do we have?
Yeah.
Yes, I meant astrophysical. Yeah.
Any kind of proper accretion?
Yes. The CMB, yes, this one down here, yeah. And so here is my answer. I'm sorry, it's already given away. We have this huge cosmic ray spectrum, right? So the cosmic ray spectrum extends from 10 to the 20 electron volts. And therefore, long before we built IceCube, we knew that there are going to be astrophysical neutrinos with extremely high energies. And here is supernova 1987A in terms of the energy of the nucleons involved in the process. So 10 orders of magnitude higher, the cosmic ray spectrum extends. And that's why theoretically, it was clear all along that there are astrophysical neutrinos at high energies. Okay, I'm afraid this can become a problem later, that I don't have mine.
So what's the problem? You don't have
My presentation has, I haven't given you the correct PDF. So can I quickly do this now?
Yeah.
Send you in.
Let's have like a 5-minute break or so.
Yeah.
Yeah, let's have a 5-minute break. Okay. Okay, everyone. Woo. So let's continue. Problem solved.
Yeah.
I can continue.
Okay, we can continue with the cosmic rays. So I wanted to just remind everyone that up here we have cosmic rays most likely produced in the sun. We see 10 GeV cosmic rays in coronal mass ejections. Then up to about the knee, we have cosmic rays which we think come from galactic supernovae. And then we have cosmic rays up to 10 to 20 electron volts in energy. And those, they are a long mystery. I started working almost 10 years ago. We didn't know where they came from, but even 50 years ago, they knew of these cosmic rays and didn't know where they came from. But we know that they're producing neutrinos. So one important thing, even though we don't know what the sources are, we know that at about 10 to 17 electron volts, the cosmic rays that come from our own galaxy, this is the diffuse cosmic rays in the disk of our galaxy, must end. And how do we end? Beyond that, we see a lot of cosmic rays, and we don't know exactly where, but somewhere around 10 to 18 electron volts, a new component must be starting, which is extragalactic. And this is just a line I drew. I don't know if it's here. How do we know they're extragalactic? Well, this is a concept we will come back to again today several times. The simplest criterion for whether a cosmic ray can be produced in a particular environment is whether the magnetic field of the source is large enough as to contain the source. Think of the LHC. So you need to have particles whose gyro radius, whose Larmor radius is small enough as to fit in that accelerator. And so in the ultra-relativistic limit, otherwise we have here the velocity of the particle in the classical case, but so now for an ultra-relativistic cosmic ray with energy E and charge number Z in a magnetic field B, the Larmor radius, this is the Larmor radius, where if I normalize it, so from rotation measures of pulsars, we know what is the magnetic field in the disk of the Milky Way. It's about 3 microgauss. And so, and for the typical size of the disk, which I've put here, order a kiloparsec, particles with energy exceeding 10 to the 18.5 electron volts cannot be contained in the magnetic field of the Milky Way. This doesn't mean, maybe there's a transient like a GRB one day in our galaxy. So it could have been that there was a source of ultra high energy cosmic rays one day. But all these cosmic rays that we see coming from all directions must be extragalactic for that reason. And we have observational absolute confirmation of this, and that's the fact that we don't see cosmic rays coming from the galactic plane. We'll discuss this again when it comes to the neutrinos. So observationally, the picture tells us that these have to be extragalactic. So how do we get neutrinos from cosmic rays? We get them primarily, today I'm going to talk only about this channel, through photopion interactions. There's another way, which is if we have a gas in the sources, this we'll discuss on Wednesday, but if we're thinking about propagation in intergalactic space, a proton which has an interaction with a photon of sufficient energy produces a pion, and either it's a neutral pion, in this case we get 2 gamma rays with energy 1/10 of the parent proton energy, or we get a charged pion which then decays to, and the muon further decays, and we get 3 neutrinos. And each of the neutrinos carries 1/4 of the pion energy, or about the 20th of the energy of the original proton. And that's a number we will use a lot today for some order of magnitude calculations. So these are the main channels, and that's why the cosmic ray spectrum told us that we have to have neutrinos up to very high energies in the early days. And so how do we detect these neutrinos? At the moment, the state of the largest detector for astrophysical neutrinos is, of course, IceCube, shown here. So it's a cubic kilometer volume detector deep in the Antarctic ice with 86 strings of multiplier tubes. And you see that it's deep in the ice because we want to shield from one of the important backgrounds, which is cosmic ray muons. In addition, there used to be another detector in the Mediterranean Sea. This has now very recently stopped operating. This was the Antares detector, and it was roughly the size of this here, Amanda, the precursor IceCube. But this also, this also uses the Cherenkov technique for the detection of neutrinos, just like we saw with Kamiokande. So here the detector volume is ice, or it could have been seawater. What we have is a neutrino. If it's a muon neutrino, it might interact somewhere outside the detector. If it's an electron neutrino, it interacts inside the detector. And then what we see is the Cherenkov light produced by the propagation of the muon for the electron inside the ice. And so the color of the PMTs tells us the timing. And so, I mean, the color shown here. And so from that, we know the arrival direction of the neutrino. And I just wanted to flash that there are several efforts currently underway to build IceCube size detectors in different parts of the world. So there is one which is almost complete in Lake Baikal, another in the Mediterranean, which they had quite a lot of deployment this year. And there is a proposal to make one also in the Pacific Ocean. So in about 10 years' time, we're going to have approximately 4 IceCube size detectors in different parts of the sky. And IceCube is going to upgrade. We'll talk about that on Wednesday. That's also going to grow. So lots of neutrinos. And so how do we detect astrophysical neutrinos? Here, I just want to remind you that we have a problem with backgrounds. So I already mentioned that cosmic ray muons are a background. In some sense, we can shield from them either by building ice cube very deep in the ice or by ignoring muons that are coming from directly over from the, let's say, from the, if I'm ice cube, they're coming directly at me, I mean, in this direction. And so if we're looking instead for neutrinos that have traversed some amount of Earth, then we can be sure that these are not muons anymore. So we shield from the muons. What we cannot shield from, this is an irreducible background, is atmospheric neutrinos. Those are neutrinos that get produced in the interactions of the cosmic ray muons, and they look individually identical to those which are astrophysical. But the only thing we can do is then make an energy-dependent statement. So the atmospheric neutrinos follow the cosmic ray spectrum precisely. So we know their spectrum. At the same time, we know that from astrophysical acceleration, the kind of power law that we get does not follow the shape of the cosmic ray spectrum that we observe at Earth because of propagation effect. So even before IceCube had seen any astrophysical neutrinos, it was known that the astrophysical neutrinos at some energy, high enough energy, they should pop up above the background. And that's shown in this plot here. Note, however, that they pop up with extremely low flux, and that's why we needed a kilometer cube detector in order to see the first ones of those neutrinos. This is what IceCube saw in 2013 when they announced the discovery of astrophysical neutrinos. So they made a very precise measurement of the atmospheric neutrino spectrum. These are the neutrinos from cosmic ray interactions in the Earth's atmosphere. And then at higher energies, you see up to about 10 PeV, 10 to the 16 electron volts, they saw a flux of neutrinos with a different spectral index. So that's how that was the signature of the discovery of astrophysical neutrinos of very high energy. And this is their distribution in the sky. So this is in galactic coordinates. So here would be the plane of our galaxy where we see all the stars, okay? And the fact that the neutrinos that we see in IceCube do not come from that plane of the galaxy where all the stars are, all stars and supernovae are mostly located, is very important. It tells us about the origin of the neutrinos, that they are not galactic. Okay, does that make sense? So the fact that we see neutrinos from directions in the sky where there are no galactic objects tells us that the majority of neutrinos that IceCube sees are extragalactic. And we'll come back to this point. This is the same with the cosmic rays. Now, how does IceCube know what flavor of neutrinos we see? Similar to Super Kamiokande, a muon traversing IceCube has sufficient momentum that it produces a track. It travels for, it's a through-going muon, it travels for a long distance inside the detector. And so we see a beautiful track like this. An electron suffers multiple scattering when it's produced. And so what we see is a fuzzy thing like this with poor angular resolution of order 10 degrees. For a muon, it's 1 degree, more or less. So those of you who are astronomers might have seen this before. This is the SIMBAD database. So you can go and put in the coordinates of your favorite astrophysical object. And then it tells you what object is in that direction. So I put in the coordinates of one of the IceCube neutrinos here. And I put the angular error of that electron neutrino, which was about 11 degrees. And what I found was 100,000 objects. These are mostly galaxies, also many stars. So if we have an electron neutrino and we're looking for the origin of that neutrino, it's a really impossible exercise. Okay, so we have too many objects. Yeah. Now, if this had been a muon neutrino and we have a 1 degree angular error, there are still 1,000, more or less. These are galaxies. So still, this is a really difficult thing what we're doing because the universe is a big place and there are a lot of possible sources for any neutrino. So I want you to remember this every time you see, a coincidence. You have to remember what is the false alarm probability. It's quite high because there are a lot of background sources. Yeah. Oh, you should.
So it's like 1,000 objects. But if we exclude stars, it should be a lot because like Gaia, and I think we should only do like Jeremy and chance and other objects. How many are left after?
Yeah, that's a good question. GRBs are not listed here. Optical transients, so I would say everything like a tidal disruption event and so on should be included in this list. On average, there are about 10 at the moment, optical transients for every neutrino. And now imagine in a year's time, we're going to have the large synoptic surveys, there's going to be 100. So it's a good point. We should not take the stars, but we still have a problem. Okay, good. So IceCube sees primarily atmospheric neutrinos. So this is what IceCube sees in the year. There's not much astrophysical sources here. It's an isotropic sky, and so this is a galactic projection. So IceCube is about here, seeing out the universe, and we have an effect which has to do with the effective area of the detector being different at different declinations. And this is why we see fewer neutrinos in this direction. But correcting for that, we see a very isotropic sky. This is about 100,000 neutrinos per year. And we know statistically from the spectrum I showed before that about 100 of them are astrophysical, but at low energies, there's no way to know if a particular neutrino is astrophysical or not. At the highest energies where there is no atmospheric background, then we can say with high probability that the particular neutrino, if it has energy 300 TeV, it's likely astrophysical individually. And so those highest energy neutrinos are the high quality signal of IceCube, and they get transmitted to all the world in real time, and then telescopes point to see if there's something peculiar happening. Okay, that's about 10 per year. This is again the same, just a different plot showing the same things that I said before, that the flux is basically isotropic in the sky. And the fact that we don't see a concentration around the galactic plane puts a limit to the total fraction of the IceCube flux that comes from the galactic plane of 15%. That's the upper limit. And so in addition, if one takes all these high energy neutrinos and looks for associations with particular populations of sources, there have been a few analyses that found something of the order of 3 point something sigma, but there's nothing yet which exceeds all others, or which goes to 5 sigma. So far, we don't know what the sources of these neutrinos are. Now, what else can we do when we have this very isotropic sky map that I showed, and we're desperate to find the sources of these neutrinos? We could have like a clustering algorithm running on our data set. And that's what has been done by the IceCube collaboration. So here, they've done 2 types of searches. One is looking at specific catalog sources which were chosen a priori. So there is a catalog of sources, and there is a search whether there is an excess of neutrinos in any of these directions, or just looking blindly at any location in the sky. And so by running this clustering algorithm, what has been found so far is a few hotspots, which after correcting for trials, they're at the moment at the order of 3 sigma. And one of them is interesting. It's the near, I think I forget, it's about 0.5 degree. Anyway, the error circle of the neutrino contains one of the nearest known active galactic nuclei, NGC 1068. And we'll talk about this galaxy a little bit on Wednesday. So this is interesting, not yet very significant. Another point that we will return to today is that even if IceCube doesn't see a point source of neutrinos, we are still learning something important about the sources, and that comes from knowing the sensitivity of the experiment. So if I look at a particular declination and I see no point sources, I can put an upper limit to the flux of any point source in that direction in the sky in terms of neutrinos. And that's what's shown in this plot. So the dashed blue line, okay, this is dependent on my assumptions of what the neutrino spectrum should look like. So for what I'm saying here, that doesn't matter very much. Let's assume we know that the neutrino spectrum should be in e⁻³ power law. Then I need to look at this curve to learn that there are no point sources anywhere in the universe with flux corresponding to a flux at Earth higher than this dashed line. So this is the sensitivity of the experiment, and we can use this, and we're going to use this later today to infer something about the sources of these neutrinos. And you see here that in the southern hemisphere, the sensitivity of IceCube is poorer just because we need, the effective area is different because we only can consider contained events. Otherwise, we have background of cosmic ray muons. And so the sensitivity is significantly better in the northern sky. So the neutrinos are foregoing. All right. This brings me to summarize the first part, which was this basic experimental findings of IceCube. So what I hope I've conveyed so far is that we know so far two astrophysical sources of neutrinos, the Sun and supernova 1987A. And we know that there is a flux of high energy neutrinos seen with IceCube. This extends up to about 10 keV in energy, then that's 10 to the 16 electron volts. But we don't know what the sources of that astrophysical flux are yet. And that's going to be what I'm going to talk about for the rest of these lectures. What might be the sources? So now I'll switch to talking about what do we know that are the properties that the sources of these neutrinos have to satisfy. Okay, so even though we don't know what the sources are, we know certain criteria they have to satisfy. And so here I will talk about a simple criterion about what does it take to accelerate cosmic rays such as to produce neutrinos in the energy range that IceCube observes them. And then we'll talk about what's a possible connection to ultra high energy cosmic rays. And then we'll come to something else, which has to do with the number density of the neutrino sources, which is another interesting clue. So let's start with the first topic, which is what does it take to accelerate neutrinos to the energy, up to the energy that IceCube detects. So here, again, we're not going to go deep into the theory of cosmic ray acceleration, but just a simple dimensional argument. So the minimum requirement, as we said about the Milky Way, in order to accelerate cosmic rays in a particular source is to confine them in the magnetic field of that source. And that's why at Earth, here it's a teratron, and I should have put the LHC there, but we can only accelerate protons to TeV unless we build a much bigger tunnel or unless we have the technology for much better magnets. So we're limited to so if we rewrite the Larmor formula, we get the maximum energy of cosmic rays that can be accelerated in a particular detector. So the product of the magnetic field in the LHC times the radius of the LHC tunnel times the charge, which is in this case 1, because we're dealing with protons, gives us the maximum energy of the protons in that detector. Similar, if we put here the radius of the moon, there was a year ago an idea that we could have an accelerator at the surface of the moon. then we get about EV just because of the diameter of the moon being large. And if we were to put these magnets in the orbit of Mercury, then we could get 10 to the 20 electron volts. Okay, that's how we could do it. Good. So now, to turn the argument around and say, what sources do we know already in the universe that fulfill this requirement? So remember that, so IceCube has seen neutrinos with energy up to about 10 PeV. There was one flash event, some 6 PeV I put here. And a neutrino takes a 20th of the energy of the proton that produced it. That means our accelerator must be accelerating protons with energy 10 to the 17 electron volts. Okay, not ultra high energy cosmic rays, 10 to the 20 electron volts, but very high energy cosmic rays. So, and we know from the Larmor formula that for a particular magnetic field and radius, we can achieve a particular maximum energy. So here we have the size of the source, the apparent size of the source, and here we have the magnetic field strength increasing in this direction. So sources which fulfill a product of magnetic field and radius such that they are above this blue diagonal line can produce 10 to the 17 electron volt protons. And so if I were to put the LHC here, it doesn't produce 10 to the 17 electron volt protons. It doesn't have the required V times R. If I put the Milky Way, okay, if I wanted to plot the Milky Way, this is a very complex issue. What exactly should I put the disk or, but okay, I think I took the size of the disk here for an approximate estimate and an average magnetic field just to plot it somewhere. So more or less, it could get to about 10 to the 17 electron volts. What other sources? There are neutron stars, so they have a radius of about 10 kilometers, but a very, very high magnetic field. Gauss. So they could very comfortably accelerate. Well, okay, they could satisfy this criteria, I should say. Whether they could accelerate is another topic. Then there are GRBs, gamma ray bursts. We'll talk about them in detail on Wednesday. So they are the jetted explosion at the end of the life of a massive star. And associated with those are also time disruption events. What happens when a star crosses close to a black hole of supermassive, but not the most massive black holes. So in these explosions or cataclysmic events, also the magnetic field strength and radius of that region is large enough that we could have easily fulfill this requirement. Then there are a type of galaxies which have a stronger magnetic field than ordinary galaxies. These are starburst galaxies. So these are galaxies in which there is a lot of star formation. The star formation drives a sort of every supernova drives a wind around it, and the collective wind from all the supernovae drives a super wind in these starburst galaxies. So they also are good sources for cosmic ray acceleration up to high energies. And finally, and these are my favorite sources, there are active galactic nuclei that could maybe accelerate cosmic rays in many things, maybe in their jets, maybe close to the black hole, and so on. And okay, supernovae also probably could make it with a simple dimensional argument, maybe some other stellar transients. The point I wanted to make here is that in reality, we don't have to satisfy this particular confinement criterion. We have to have an acceleration mechanism, some kind of theory. How could these particles get accelerated? And so the simplest mechanism is shock acceleration, so Fermi type acceleration. And as it so happens, the expression for the maximum energy in the absence of any severe energy losses is this expression here. So it's essentially the Hillas expression, but it also is important to consider the velocity of the outflow. So this is the velocity in units of the speed of light. And there is a prefactor here related to the type of scattering. So the turbulence in that region where the particles are crossing the shock and being accelerated. So if I put these prefactors in for a source which is not expanding at the speed of light, but somehow 0.01 c, you see that things like supernovae and normal galaxies also are really challenged. So my conclusion here is this: there are many astrophysical source types that could be producing these neutrinos that IceCube sees, but most likely it's not standard galaxies, and most likely it's not standard supernovae, even though there are a lot of supernovae that could do the job. But it's maybe something a little more exotic. Okay, I think maybe this is a good place to stop, even though we're a bit early. Is this okay? If I stop here and take questions, and then so we're going to continue with this after the break.
Questions? Wait for time.
What's the question here?
So you mentioned this turbulence factor. As far as I understand, we really struggle to actually understand turbulence very well. So is this some sort of just holistic modeling argument, or just put some number in and try to?
This is an optimistic limit, so we have some bomb type diffusion in that region. Yes, it only could get worse than that.
Questions? There was a question.
Yeah, it's just out of curiosity. I think it's like 12 or something like that. You show a plot with the fluxes, and there was 1 million of energy with not a lot of data points. Is there any reason, or are there experiments? Yeah, that one. Or yeah.
Oh, here?
Yeah, that region in between the 10 to the 12 and 13. See, not that many points that.
So first of all, this is an extremely old plot. Meanwhile, there are other experiments, but I think it also happens to be, and maybe Marcus can correct me here, the region where we have a transition from. Wait, okay. So I think there are more experiments covering this region here, and the flux is shown. So there is a transition between ground-based and space-based experiments, but I'm not sure if it's exactly here. Probably, Marcus.
I think this is one of the reasons why the data is a little sparser there, but there are actually some experiments covering this area. So for the that's much I'm not showing. So it's an old one, as you said.
Yeah. Okay.
So at low energies, you can go up into space, you can use balloon experiments, satellite experiments, but then since the flux is of course falling, it becomes less and less efficient. And then, but once the energy gets high enough, you can then see extended air showers and that's observation above. Any further questions?
Thanks for the talk. So you said that there are 2 confirmed astrophysical neutrino sources. One is the Sun and SN 1987. What about the 2017 Blizzard? Isn't that a confirmed source?
We're gonna talk a lot about this on Wednesday, and it's a 3 sigma.
Oh, okay.
But okay, supernova 1987A is also, I don't know, 3 point, so it's
Yeah,
not like
yeah.
5 sigma. So yeah, it depends on your definition, but we will talk in detail about that event.
Thank you.
Further questions? Yeah.
Uh-huh.
So I wonder why the difference between checkboard cascade so the question is about what difference occur between the thread line or cascade line
Yeah,
according to the range of the delta signal.
the range of the.
The delta between 1 degree or
Yeah, okay. I think I understood your question. So the muon that is produced in this interaction has a lot of momentum, and it just can just go through the detector and even continue. For the electron gets scattered within a very short range, and it suffers multiple scattering. So it just doesn't make it very far, and it deposits all its energy. So because we have a big handle in the ice cube detector, we can reconstruct the arrival direction quite well. We have a big baseline of the entire detector in this example. Here, we just see a blob in ice cube. It's harder to know exactly where it started. There isn't enough. You see, the energy gets lost really fast. On the other hand, here we have a perfect colorimetric measurement of the energy of the neutrino, whereas for the muon, we might have lost some in the initial parts. And this is very difficult when you're doing modeling and you want to know the energy of the neutrino. Ice cube cannot always tell you, can only tell you a lower limit.
Another question?
Once again with the gray sources, because on the the energies at 10 to the 20 electron volt, the flux is so small that you figure it is written that it's exactly 1 particle per square kilometer per century, right? So how do we check that?
Okay, that's an excellent question. So what do we need? We need the detector. Can we change here? We can't change the flux. We can only change the size of the detector. So now think of a 1,000 square kilometer detector. So we'd see a 10 particles per century. So it exists. Okay, so in Argentina, there is a particle detector which extends 3,000 square kilometers. That's called the Pierre Roger Observatory. We see the air showers. We don't see the cosmic rays. We have to wait a long time. But the air showers several kilometers in extension. So we only need 1 detector per kilometer.
I'm just going to read one. There's one question online from Ruth Badnega. What might the track of a neutrino look like?
Ooh, that's a nice question. So a tau neutrino can look something like the electron neutrino. I'm sorry, I've gone through all my slides. So it can look like a cascade, what we saw before, or it could have a double bang, which is, and this has been observed in ice cubes. So it could have a first shower from the original interaction, and then another one after the tau electron decays. So you have 2 cascades, and then if you have 2 cascades, you have a better angular resolution.
Another one. Marco Hoffman has a question. Marco, I think you can type it. do we not hear people on Zoom? I think not. Ah. Okay, might take. Yeah, maybe we can come back to this after
Yeah.
the coffee break.
Marco, let's come back to this later. That's okay.
Okay. Then there will be time for further questions after the coffee break. So let's thank Foteini again.